Okay, good afternoon, dear colleagues. In my presentation, we will travel from our so nice and mild Australian winter to the real Russian winter to the heart of Siberia. It's not Moscow. It's I will describe the place later. And now a few words about motivation. The idea of our study was to fill even two major data gaps in urban climate science. The first gap is geographical. Despite many years of urban climate research, there is still a lack of studies for high latitude regions, including Siberia, Arctic, Alaska, Canada, and so on. Because big reviews like these studies even ignore these regions, but in these regions we still have quite big cities. And we have very specific impacts of urban climate features there, such as impact on permafrost degradation and on air quality during very strong winter inversions. And another gap was very nicely introduced in yesterday's lecture by Simon Kurhaus. Uh, so it's well known boundary layer gap because we have a lot of observations near surface, some observations in the troposphere, but very limited data in boundary layer. And our study is here, so we will try to do something with these two gaps. Together with our colleagues, firstly with Pavel Konstantinov, we spent some time during last 10 years for making urban climate research in high latitudes. So our previous studies were focused on near-surface climate. We installed urban climate network in 6 Russian Arctic cities and discover some nice results, including strong heat island observed in winter. We use several methods, including weather stations, low-cost sensors, car-based sounding. Also, our results were further confirmed by remote sensing by our Norwegian colleagues. And in this study, we will go from the surface above to the urban boundary layer. So this is study area, not Moscow, much smaller, but still quite a big city with about 50,000 inhabitants. It is called Nadym. It is located in western Siberia, the area where Russian natural gas is produced. And it is really cold climate city because mean winter temperature is minus 21. Mean temperature, not minimum. And in this city, we have several intensive observation campaigns to study its effect on boundary layer. Actually, we have 3 types of campaigns. In the first one, we install microwave temperature profiler in the rural site near airport and try to make drone-based sounding in the city center. It is a DJI Phantom quadcopter with some meteorological sensors. It was quite difficult, so we made quite a little number of measurements, but we come next years with more drones, with 2 drones, and make more observations simultaneous observations in the city and in the rural side. And we also have supporting observations in the urban canopy layer by low-cost sensors and weather stations. And this is an overview of our experimental campaigns. So all 5 campaigns in one time axis. So this is the first campaign, the longest one, and probably the most interesting one, because here we found we observed very intense cold wave, when temperature drops in one day from minus 10 to minus 45. And we were lucky to make drone-based measurements during this period in the city. And you can see that this color shading, it is urban heat island intensity. So we have urban heat island of about 5 degrees during this cold wave. So minus 45 outside and minus 40 in the city, much warmer. And this is wind speed and stratification. So and next intensive campaign, we don't observe strong heat island, and then we also observe several cold waves, which were quite similar to the first one, but not so extreme. And during these cold waves, we have increase of the wind speed as expected, and increase of boundary layer stability and strong temperature inversion. So during the first cold wave, we have an inversion up to with intensity up to 20 degrees in lowest 300 meters. And this inversions here, inversion strength was observed by temperature profiler. And here we use reanalysis data, which is quite good agreement. And also this radiation balance. So it's polar night. So solar incoming solar radiation, yellow one, it's very, very small. And a long wave balance is mostly negative, and it's also negative during our events, cold events with heat island. But it's interesting that the most negative balance is before this extreme heat island cases. And the most interesting results of our drone-based sounding for the first cold wave. So here we were lucky to manage drone sounding only in the city. So this is this two different sensors and also surface measurements in the city. And in rural site we had temperature profiler. This is its original readings, and so there is quite disagreement above the boundary layer. But it is a typical problem of this equipment, and after making such correction, we see quite good agreement above the boundary layer height and boundary layer very thin of 50-100 meters where we have heat island. And this is wind profile estimated by our drones. And also we see that wind speed is very calm in the whole lower troposphere, but still not zero. And this is how it was looking. It's interesting that the city was covered by very dense fog with very sharp upper border. And the height of this fog layer was about 50 meters, a bit higher than the buildings, which nicely agrees with observations. And this is next intensive campaign in 2019. Here we make much more drone-based soundings in two sites, one in the city and one in rural area. But we didn't manage to find significant differences, but still quite a wide difference, about 1 degree, located again in the lowest 50 meters. And probably the most interesting third intensive duration period. Here we were happy to observe development of urban and rural boundary layers from the quite warm conditions to the cold wave, and again the increasing urban heat island intensity. So this is beginning, everything is well mixed, both urban and rural sites, and this is the last moment when it became too cold and we returned to our hotel. So this is again difference in the lowest 50 meters. And it's interesting that in the very dense urban site, which is shown as red, it's even unstable stratification and neutral stratification in urban open space and inversion in rural area. And a few last campaigns, they confirm previous results. Here we also see the evolution of temperature when the cold wave stopped, when the temperature started to rise. So and we can see that in rural area, evolution is much faster. So this arrow shows this evolution during few hours, and we have very strong increase of temperature outside of the city and almost zero changes in the city. And to confirm our findings, we make some statistical analysis. And for the canopy layer urban heat island, we have here quite long observations for two urban sites. One is dense urban site, and second is urban park. And we make correlation analysis with several predictors from Era 5, including temperature gradient in the lowest from 50 meters to 300 meters. And we find that temperature difference in lowest 50 meters or 100 meters is the strongest predictor for the canopy layer heat island, in our case, in winter. This allows to make some nice discussion, also combining with amazing results from previous lecture by Simon Kathaus. So we found quite strong heat island with canopy layer intensity up to 6-8 Kelvin, but in very thin layer. While in European cities which are most studied, there is a same magnitude of urban heat island intensity, but it is but urban boundary layer is much more high even at night. It's about 500 meters in Paris. Today there were estimates about more than 100 meters from today's presentations. And we also found that there is very clear correlation between canopy layer heat island and vertical mixing. And the same was found for Paris. So in previous studies, this factor is often, its importance is underestimated. And we show that it's very important, at least for Arctic. But other studies show that it is important for other cities as well. So this is our conclusions. I will not repeat them. You could find more details in our recent paper published in Urban Climate in beginning of this year. And the last slide, I need to thank you for attention, but not only for attention, but also for inspiration for making this study, because actually it was inspired by the presentation of Winston Chow more than 5 years ago in EGU conference. He presents some results of making drone-based measurements over Singapore. And I decided, yes, that's a good idea. Let's try to do it somewhere in Russia. And this is, so after this long story, I'm here presenting this result. And this is final conclusion from our talk. And this is we are after making our soundings. Thank you for your attention.
So any questions after that very lively discussion? Thank you. Yes, back of. Oh.
Hello, thank you very much for your nice presentation. I'm from the University of Stuttgart. We also did some drone measurements in our city where the temperatures were around 5 degrees, so not as cold as your measurements. Actually, something as compared to your measurements. We had some practical problems with the drone battery because the flight time was reduced to less than half in such cold temperatures, but I don't know what you experienced in your measurements and what did you do if you had the low flight time due to low temperatures?
We hid the drone batteries behind our codes.
All right, I think, so one more quick question, 30 seconds. Yes, Jason?
What's the air quality like with such low boundary?
It may be quite bad. This is not a case for Nadym because Nadym don't have strong industries. But other cities with strong industries really suffer from air quality problems during winter time inversions.
Wonderful. Please join me. Any follow-on questions afterwards? Please join me in thanking.